Again, my name is Amy Navickas-Brash. I am a Stormwater Engineering Manager at Osborne Consulting. I'm also an adjunct engineering professor at Gonzaga University, where I teach stormwater management and senior design. So I want to acknowledge the team that's been involved in this project since the very beginning, which has two distinct groups. We have the TAC representatives, alternatives, and other participants. We've met with them quite a bit throughout the project. We'll go through the plan that we'll have for approaching some of the work we've done, because that's really important to make sure we're on the same page with the plan and get their input before proceeding with doing the actual work. And then we come back with the findings we have and go through it with them, and have been working to develop a white paper that will work for them moving into the next phase of the study. We also have the consultant team that we've been working with. This is a little unusual in that there was most of the time I would compete with these people on projects and not team with them. And so this was a fun project to get to work with my peers and have philosophical discussions on stormwater. So the consultant team consisted of myself. I was the project manager. Maria from Osborne Consulting was also a significant part of the team. We also had Paul Fent from Parametrics, Christian Nilsson from Geosyntech, James Packman from Aspect. And for our very last TAC meeting, we'll have Christian Mueller from Cascadia Consulting Group joining us as the facilitator for that group. So it's been a huge group effort going through this, lots of debates behind the scenes. I've come to look forward to those meetings with the consultant team. I'll be sad when it's over. So I want to just outline what we're going to be talking about. I'm going to first go through just an overview of the project and also talk a little bit about the benefit questions. But as Karen mentioned in the agenda, I did a presentation that focused on the work we did to answer the benefit questions for MuniCon. So I've been asked to not spend too much time on that and instead refer you to the link for that. It is on the Washington Stormwater's website, as well as YouTube has it, and you can watch it. It's very exciting. So for this presentation, I am going to focus primarily on the application questions, but in order to make sure we're all on level playing field and understand where I'm coming from, I am going to go through some of the things we did in the benefit questions, because it's really important on how it informs how we answered the application questions. And it also helps highlight the information we did and did not find. So the main goal of this particular project is to develop an objective science-based approach in white paper. So we basically, our job was to go out and find the status of research right now on the SSC projects and summarize that in this white paper. The white paper will be used in the future to help inform future SSC projects, as well as provide a basis for policy discussions with the stakeholders as they start talking about the next permit cycle and how the NPDES MS4 permit requirements for SSCs might look in that permit. So when I talk about the SSC permit requirements, what I'm really talking about is retrofitting. I'm talking about retrofitting those areas in developed areas that don't have stormwater management or have inadequate stormwater management, and reducing the impacts to watershed hydrology and pollutant discharges to the MS4 that are not adequately addressed already in the stormwater management plan. So if you think about when our permits were issued, late 90s, mid 2000s for phase 1 and 2, all the areas developed before that did not have stormwater management. So this is going back to those areas and retrofitting them and bringing them up to current standards. So just a little bit more background on the current requirements so you understand where we're coming from as we get into some of these discussions. Currently, the SSC requirements appear in the phase 1 permit. A lot of detail about it in Appendix 12 if you're dying to know more after this presentation. And that section goes through all the reporting requirements for the annual report. It defines the different project types. There's 11 different types total. For example, flow control facilities, new runoff treatment facilities, or to name a couple, restoration of riparian buffer or forested area. So it provides a description there, also talks about what a non-qualifying project is. For example, anything below the ordinary high water mark wouldn't count toward the SSC requirement. In the appendix, it does provide information about the program points and multipliers. And so the first part of it starts off with the SSC number, which is 1 through 11, what that particular SSC is striving to achieve. And then it also provides SSC multipliers, which help with scaling the benefit that's anticipated based on the type of SSC that's being used. Let's see. Another thing to know is that currently in the Phase I requirements, the Phase I permittees are striving to achieve 300 points by December 31st, 2022. And of those, 225 can be design stage, and a minimum of 75 need to be complete projects or maintenance stage types of projects. This appendix also provides instructions for how to calculate the points that you need to get, information about the multipliers, also looking at equivalent areas. So if you don't have a full-size BMP, looking at what that represents, and the equivalent area or length or just area. So the main project elements that we had here in order to achieve that goal, we had 4 main areas we were focused on. The first one was to define the requirements and goals and vision for the project. So that'll be in chapter 2 of the white paper. For this one, we went through all of the permits in Washington State, all the way back to the beginning, to really outline when the first SSC requirements started and how they've evolved over time. We did go all the way back to EPA because they are the ones that are requiring these, and provide a summary about that. We also interviewed Ecology to develop a better understanding of the reasoning for the current permit language. And we interviewed several jurisdictions, both Phase I and II, to get a better understanding of their municipal program. And we use that information to really help focus our literature search, because a lot of information out there, we want to get the information that's most relevant to them. So another big part of the study was to develop responses to benefit questions. And these are a series of questions that were developed prior to the consultant team starting the project. And they're related to determining what is the benefit of the different SSC project activity types related to the stormwater environmental benefits, looking at impacts, and what types of metrics are used to measure those benefits. We also spent a lot of time on developing responses to application questions. So these were a series of questions that were also developed prior to the start of the consultant team. And they were related to the literature that we found that focuses more on how to apply that information or how it's being applied currently. And then the last part of this is going into the policy discussions, which we'll be wrapping up next month. And this is really focused on a transition plan. So we've been focused on this study on developing this white paper and developing a summary of the current status of literature related to the SSCs. And now we're going to begin transitioning it so it can begin, the policy discussions can begin. So the only portion of our contract that carries in is this transition plan and helping to form this charter workshop. We'll begin talking about the next phase and looking at the minimum level of SSC effort that's going to be required in the next permit, as well as the best ways to measure and assess the effectiveness of the SSCs. So one of the first things we decided to do was define some key terms. There was a lot of terminology that we were going to use and a lot of terminology we needed to make sure we were all on the same page with. So we spent some time defining terms. Starting down with the contributing basin areas. This is the area that's discharging runoff to the SSC. So within that, of importance to us was to understand the impact factors. And these are variables within the watershed, within that basin area that can influence the performance of the SSC. Some of those examples include land use, soil type, topography, as an example. So from the contributing basin area, that's going to discharge right into the SSC BMP. And with that, we also looked at performance limitations. So we're really trying to understand what are the variables that can influence the SSC performance with the impact factors and the performance limitations. Performance limitations are features of the SSC itself that can influence the performance. So some examples of those would be the type of BMP that's selected, the sizing criteria, the infiltration rate, the media thickness, for example. Another important variable was both the flow control and treatment mechanisms that the SSC provides. So examples of that for a flow control mechanism would be some type of control structure that's regulating the discharge of flow from the BMP. Another example would be a treatment mechanism that has like sorptive capacity to help remove dissolved metals. So what are those mechanisms that can be expected with the SSC BMP? So then we start looking at the benefits. We considered these variables that can influence the benefit. Now, what are those benefits that you might expect to see? So the two we looked at that are stormwater related in the permit are the hydrology benefit and the water quality benefit, where the hydrology benefit related to the SSC is the effectiveness of the SSC for reducing flows, where the water quality benefit is the effectiveness of the SSC for reducing target pollutants. The other thing we also looked at was other environmental benefits. So these are not items that are in the permit, but some other benefit that the SSC could be providing that could improve conditions within the watershed area. Some examples of those would be groundwater recharge, air quality improvement is another one. And with that, we also were looking at the metrics. What are metrics that are used both in Washington state as well as nationally to measure this benefit? A percent reduction is an example of a metric that could be used. And we also define the performance indicators related to the SSC, focused on the hydrology benefit and the water quality benefit, and how effective the SSC is for reducing pollutants or whatever metric is selected. It's important to note that we define the point of measurement for the performance indicators as the discharge point of the SSC in general. So our approach for doing this work included a lot of literature reviewed. So we reviewed the Phase I annual reports to understand what types of SSC projects have been done in the past. We wanted to make sure we were focusing on our literature search on ones that were most relevant to the permittees indicated by ones that are maybe used more commonly. We also had interviews with the permittees and asked them about ones they might anticipate using in the future to help us narrow that focus. Met with Ecology again to really go through and understand the permit, the reasoning for the permit language currently. Reviewed a lot of journal articles as well. Some were single studies where the whole paper was about one study, and some were a synthesis of many studies. Gave priority to peer-reviewed studies because those tend to have higher data quality. Also reviewed government reports and documents. So these would be reports that are on a government website or government agency's website. These are usually peer-reviewed as well, although it's not always as clear depending on where you find the document. And we also pulled data from the International BMP database and NSQD to help with synthesizing all of this information. Prior to starting the work, we defined an approach for the literature search. We wanted to have comparable data so that when we were going through this, so we were comparing apples to apples. So we laid out a plan. Starting on the left side of it, the top part is our plan, the bottom part is what actually happened because it didn't go as planned, and I'll explain why, and then I'll explain to you why that matters to the data. So starting on the left, what we started looking for is studies that were conducted in Washington was a big preference because those studies are more likely to be done on BMPs that are in the ecology manuals or other equivalent manuals in Washington state. So they're more likely to be comparable BMPs. We were also trying to find studies with similar like climatic conditions or similar BMPs when we were going through. So we had that comparability with them, really wanting to understand the different variables that may be influencing the performance of the SSC. But what we actually found is there really wasn't enough information to determine if there were similar conditions. So we had a difficult time comparing the two. And prior to starting that literature search, we had a rather large template. We went through to collect consistent information so we could do this. And we just could not find enough information to really compare whether conditions were similar. And there weren't enough studies in Washington that we could use for this project alone. Another part of this was to identify the impact factors that may be influencing the results for the different SSCs. That was important to us. We wanted to try to figure that out and maybe start getting some insight into how the weight factor might be influencing performance and where those weight factors come from. But what we found is most studies don't talk about those impact factors in enough detail for us to understand how they're the same or different between studies. And when we got to that point, we reached a point where we realized that we're not going to be able to quantitatively understand how those contributing basin conditions, those impact factors, can influence the performance indicators such as the percent flow control reduction or percent pollutant reduction. There's not enough information to really get to that. We do know enough about the literature, though, that the conditions we've identified are important and they do influence the performance. So we were able to develop a qualitative assessment I'll show you, that just helped guide some of the information and helped us, especially in the approach section. Another thing we're looking at is trying to find studies that were conducted following the TAPE research protocol. The reason we were picking that is TAPE really has a robust program to develop quality data. It provides comparability between studies as well. And we were looking for that. And what we found is there weren't very many studies conducted by TAPE that were relevant to what we were doing, or the study didn't provide enough information for us to understand if they did something similar to TAPE. So that was a challenge. And I'll explain why that can be very important in a minute. And the last is just BMP comparability to Washington, especially Western Washington BMPs. Not all BMPs are the same. A swale in Washington state, the design criteria for that may be completely different when you go to the East Coast. It varies, and what they call the BMP isn't universal. So we were really trying to make sure we had comparable BMPs, but it was very difficult to do that. We were not able to accomplish that in the study. Wasn't enough information described to determine that, not enough Washington studies for us to conclude that. So why do some of these things matter? Well, let's talk about the impact factors a little bit. And I won't go through all of these because I see, am I done at 10:30, Karen?
You have until 10:35 if you want your whole hour, because we were 5 minutes late.
Okay, thank you. So looking at the literature search related to the impact factors, I'm thinking about these more qualitatively. So in the first column, we have the impact factors, and it's just some of the ones that I have listed here. These are, again, are conditions within the contributing basin area that can influence the performance of the SSC. Examples are land use, would be one, pollutant sources, infiltration potential, topography and land cover, and climate conditions. The next column, we have the influence on the stormwater characteristics, again, qualitatively, and the potential influence on the SSC related to the benefits. So just looking at land use and pollutant sources, both of these, land use can influence the pollutant types and loadings. Pollutant sources can influence the influent pollutant characteristics, such as the type of pollutant, concentration of the pollutants, the loading of the pollutant. So how that can influence the SSC, it can influence the influent characteristics. So the concentration, the stormwater chemistry can change based on those conditions, which will influence the treatment mechanisms that are needed to reduce pollutants. And SSCs have different treatment mechanisms. They're not all the same. So some are better at targeting different pollutants than others. So it was really important to identify those going through. Infiltration potential. So in that contributing basin area, it can influence the quantity of stormwater runoff. So as most of us all know, the higher the infiltration rates, the less runoff I'm going to have. And which will increase the hydrology benefit of the SSC, and the lower the runoff, it will increase the hydrology benefit by reducing the runoff flow rate and volume through infiltration, and conversely, if we had low infiltration rates. So topography and land cover, that can influence the flow rate of runoff, and the climate conditions can influence the rainfall intensity, duration, and depth. Where runoff, specifically runoff volume and flow rate, and the energy available to transport pollutants. So when you have flatter areas, you don't have as much rainfall energy that's going to move pollutants downstream than you do when you have steeper areas. So this can affect the SSC type, placement, and design, will influence the ability to reduce the basin flow rates and pollutants there. So this is just more of a qualitative consideration, especially as we start thinking about those application pieces for the SSCs. Okay, so as part of our approach for the literature search, we looked at tape protocol. I want to explain why this is really important when we're thinking about comparing data between studies. So this is from the International BMP database. It's just looking at dissolved metal. On the y-axis, I have the frequency that a specific reduction occurred. So 0% means there were no reductions in that category, and 100% means all of the data had that reduction. So you can see, looking at all data here, there's about 5% that actually had an increase in dissolved zinc coming out of the BMP. Then you've got about 30% that had no change. You had about 15% that had less than 20% reduction. You had about 10% that had a reduction of 20 to 40%. And then about 10% that had 40 to 60%. And then about 20% that had 60 to 80% reduction. And then the last 15 was greater than 80%. So these were all treatment BMPs that would fall in SSC type 2 for new treatment BMPs that we looked at. And we looked at all of them. We didn't filter anything out. Then what we did is we broke the data up and we looked at 3 different groupings. We looked at the tape influent concentration range first. And tape defines the influent concentration from 0.02 to 0.3 milligrams per liter. It limits the influent concentration to that range. And then we also looked at concentrations that are higher than the 0.3 to see how the pollutant reduction compared. And we also looked at studies that were done where the influent concentration was less than tape. And what you see is essentially the lower the influent concentration, typically the lower the reduction that you see in the BMP or the SSC, where the higher the influent concentration, the greater reduction you'll see. So you can see that where studies that were done where it was over 0.3 milligrams per liter, you had 65% that, or 55% that had a greater than 80% reduction, compared to the study that had less than 0.02, less than the tape range, which had less than 10%. So the dirtier stormwater, typically the higher pollutant reduction you're going to see. So we were hoping to find studies that were done with influent concentrations closer to the tape range. That was very difficult to do. We ended up going into the International BMP database and just limiting the studies down to focus more on the influent concentrations in that range. So another thing to consider is the literature search with regard to comparability. Again, we wanted to compare studies that were done on BMPs that were like Western Washington because they're not the same nationally. So here's a really good example of how they vary and how that can influence the data. So on the left, we have a study that was done in 2015 in Western Washington. This study was done on the 60-40 bioretention mix, which has an 18-inch depth. And looking at the effluent concentration, what they concluded in the study is they had about 209% of nitrates leaching. So this media leaches nitrates, which most of you probably are aware of that. 2 studies that were done in New Hampshire looked at 2 different depths of media. It had a different media composition as well. And they looked at the nitrates that were reduced, and they actually got a 44% reduction and a 43% reduction. They were not, and they didn't report any leaching from these studies. These are very different results. These are also not comparable BMPs because it's a completely different media, completely different depth. I'm not surprised to see these differences here. We know that the Washington media leaches nutrients. The other one appears not to. The different depths are also important. The deeper your media depth, typically, the more likely you'll see nitrogen cycling, which is often the dominant mechanism for reducing nitrates. So we also noted that some studies don't include leaching at all. They don't mention that. We do in Washington, we note when we see pollutant leaching out, but I did see some that were just not noting it. So, which when you don't include that data, it artificially raises the percent reduction. So anyway, so these are the reasons we outlined having this consistent approach at the very beginning of the study, but the literature just didn't exist for us to be able to follow the plan and collect data for the study. So let me show you what we found in the study. So in the first column here, I have the SSC project activity type, numbered all 11 of them. And then I have our different performance indicators. We have hydrology that we used, as well as water quality. Again, this is the effectiveness of the SSC for reducing flows or reducing pollutants. We looked at all of the targeted pollutants that are in the NPDES MS4 permit. We looked at the performance indicators for those for each SSC. And then we also looked at the TMDLs that are listed in the Western Washington permits to see if there was data available to indicate how these performed, how these SSCs would perform for those different parameters. So here's what we found. NA means it just didn't apply to that study. So for example, for new flow control facilities, we weren't looking for the NPDES, anything in the permit, because it's not approved to provide any reduction of a pollutant. So we didn't look for that in the research. The same with new runoff treatment BMPs, not approved to provide flow control reductions. So we didn't have that either. So we had a handful of items that we didn't look up at all because they're not approved to be used for that. The next thing we did at the very beginning of the study with the TAC, we talked about the SSCs that are also in the stormwater manuals, like flow control facilities, runoff treatment facilities, LID, and decided that instead of going through the literature and looking up information about the performance of the SSCs for regulated parameters, what we would do instead is use the performance standard for runoff treatment and flow control that's in the manual. So those are the parameters that are the data that we used for that. From that, going through the research, wanted to give you an idea of how many studies we found that had greater than 10 samples in the study. Those are primarily within the TMDLs. I found quite a bit. Most of that was from the International BMP database, and for the flow control, runoff treatment, and new LID BMPs. For studies that had less than 10 samples within the study itself, there were quite a few relating to retrofit of existing treatment or flow control facility, restoration or riparian buffer, and other actions addressed to address stormwater runoff into or from the MS4 not otherwise required in the SSC requirements. What was challenging with some of the studies is that the information was available below the ordinary high water mark and not looking at the discharge point of a BMP or SSC. So that made it challenging to find information as well. We also had, well, we couldn't find information, but we used substitute data. Good example is property acquisition and removal of impervious surfaces. So we were able to use data from open spaces and compare that to what we presume the property would be if it wasn't acquired and then not developed or the impervious surface was not removed. And then just no data at all. Maintenance with capital construction costs greater than $25,000 or floodplain reconnection projects. There's some good data on floodplain reconnection projects, but it's mostly modeling work that's been done. So it's not done with samples and it's not measured at the discharge point of the SSC itself. It's measured in the water body. So after we got through all that information in the literature search, we did develop a matrices. I'll show you at the very end. It evolved as we went through the study. Any data we collected, we synthesized using basic statistics. When we had some of the studies, especially the International BMP database, I went through and tried to limit it down to the tape parameters as close as I could so it'd be more representative of what we'd seen in Washington. We recorded the performance indicators. The metric we used was percent reduction. We also recorded when it was leaching. So in the table, if you see negative values, that's because that parameter was leaching from that SSC. We noticed a pretty wide range of data because within the SSC categories, we talk about new runoff treatment BMP. That includes many BMPs, not just one in particular. And we start averaging it, you get interesting ranges of information. So we reported averages, minimum, max values, to showing you some of the differences in the data and the sample size. And I'll show you that at the very end. We also documented environmental benefits if they were included in the study we were reviewing, and identified data gaps. There were a lot of them. So we identified the status of the research as it is now. Don't remember why that showed up that way. Keep going. Oh, so I'm ending my conversation about the benefits. I'm going to switch to application now. If you want to know more information about what we did, again, that video is on YouTube. Okay, so for the application questions, the approach we took is we built upon the work from the benefit questions that we did. We did a lot of literature search. We collected information that would help inform the approach, the application questions as well. We did some additional literature search, but it wasn't very much going through this section. So because there are a lot of literature gaps related to the application pieces, it's not possible to answer most of the questions directly. So what we did going through is we talk about the status of the literature. What do we know? What do we don't know based on the information that is available? And then what we did focus on is more of that qualitative thought process. We know from reading through the literature that there are conditions like impact factors in the contributing basin, the performance or the limitations with the SSC. Again, that's variables within the SSC itself or features that can impact the SSC performance. So we know some of those things are going to happen. We just don't know how much so in relation to the SSCs we're looking at. So we identified variables that we believe can influence the answer to the application questions and try to identify going through responses, how they would impact it. So some of those conditions are the receiving water conditions, the contributing basin area again, the proposed SSC site, and the SSC project activity types that are selected. So, and I'll walk you through, we have a flow chart that we've been working on for that. So with the receiving water conditions specifically, that's helping us identify what are the flow control and runoff treatment needs that need to be addressed. And the contributing basin area also has the same with identifying the flow control and runoff treatment. And I have a, going to go last. Okay, I'll have to go backwards. So we have identifying the needs both from the receiving water body as well as the contributing basin area. And then at the SSC site itself, questions that we're answering to help figure out which SSC can go there are, is the site suitable for that particular SSC? Can you construct a full-size SSC, or will you have reduced benefits because you can't? Because with the retrofit projects, it's not the same as meeting new or redeveloped standards. You do have some flexibility if you can't fit the full BMP in to put in a smaller one. So really starting to understand how those conditions can affect the performance. And then we also have the SSC project activity type that's selected. And not all SSC project activity types are the same. They do different things. So making sure that the SSC project activity type that's selected provides the flow control or runoff treatment needed based on the receiving water basin conditions. So this is the graphic that we developed to kind of illustrate how all of these pieces go together. We have the receiving water conditions again, and that with that we're looking at identifying how hydrology and the water quality conditions and ultimately determining what those flow control and runoff treatment needs are based on the conditions in the water body. We also have the contributing basin conditions that we need to take into effect. And one is the basin impact factors. Again, those variables in the basin area that can influence the SSC performance. We need to evaluate those impact factors and their influence on stormwater characteristics, which will then help us with our SSC BMP selection. And then from that, looking at selecting a proposed site and evaluating that site to see if it's suitable for the SSC that you've selected, or which conditions are at that site to help guide the selection of SSCs. And then moving into selecting an SSC. And a big part of that is identifying an SSC that will actually provide the runoff treatment and flow control that's needed based on the receiving water and contributing basin conditions. And then figuring out what the benefit is of that particular SSC. See if there are anything about the site that's going to impact have performance limitations for the SSC and reduce the performance. For example, if you can't fit a full-size BMP there, you're going to have reduced benefits because you don't have the full BMP, and taking that into consideration when you're evaluating the benefit. And then moving into selecting which BMP you'll pick, and the most effective one would be one that provides the treatment and flow control that's needed. The site that has the least impact on the SSC performance limitations, so there's no impact on it from hitting maximum performance, and also having the highest reported reduction. So all that data we collected to see how the different SSCs, the performance indicators, looking at which one may have the higher performance. where a less effective SSC would be identified as it doesn't meet one or more of those particular items. And we have a lot of arrows in here because it is an extremely iterative process and never this simple. So, but this is just here to give you a high view of what are these variables that can influence the responses to the application questions. So I'm going to go through our responses. It's pretty much the rest of the presentation, and then we'll go through the matrices at the end. I am reading the responses and then highlighting how they fit into the table. So it's difficult when you have to, your whole project focuses on answering questions to make it the PowerPoint more interesting. So bear with me. So the first question we had to answer is, are there eligible SSC project activity types that are better suited for high quality receiving waters that need to be protected versus impaired receiving waters in need of restoration? So what we found is there are not across the board SSC project activity types that are better suited for high quality receiving waters versus impaired receiving waters. Eligible SSC projects should be chosen to address the problem at hand, be it water quality or flow control, regardless of the receiving water type. The issue should drive the solution, and multiple SSC types can be used to address similar issues depending on the treatment and flow control mechanism they provide. Project-specific factors such as the contributing basin conditions and the proposed SSC project site may result in variable SSC project activity types being more suitable for protecting or improving receiving water conditions. And kind of key points that pop up in here that I'll highlight on the flow chart again is we really want to focus on, instead of thinking about is it better suited, thinking about what is the problem in the receiving water conditions or the pollutants of concern, those impact factors, and making sure that the SSC has the right mechanisms for treatment and flow control to meet that need. So going back to our flow chart and looking at the left side, the SSC should address the problem. So those are the receiving water conditions or impairments, and the contributing basin conditions, those impact factors that can influence the SSC performance. And the other part is making sure that the SSC that's picked provides the mechanisms that are needed to address the problem at hand. That's getting to the core of that answer. So for response to question 1A, within an SSC project activity type, are there more or less effective BMPs or combination of BMPs for various land uses and receiving waters? Our response for that was there are typically multiple BMPs that fall within each SSC project activity type. BMPs that are more or less effective is dependent on many variables such as the contributing basin impact factors, the specific receiving water impairments identified for improvement, whether the selected BMP provides the type of hydrology, flow control mechanism, and or water quality treatment mechanism benefit needed, the project site suitability for locating the BMP, and other factors itself. So really highlighting in this one, the part that's important when we're talking about more or less effective, it's really going to be influenced by whether the selected BMP provides the flow control or water quality mechanism that's needed to target those parameters. And also the concept that not all BMPs or SSCs are created equally. They all have different functions. So this is a table that of more structural BMPs that fall into category or type 1, 2, and 3, which is new flow control, new runoff treatment, and LID BMPs themselves. And on the far left, we just have the BMP categories, and the BMPs are broken up by that. We have the BMP name itself broken out from the SSC category. Then we note the different flow control and treatment mechanisms that are provided. And you can see for flow control, some of them provide flow control, some don't. Some of them provide basic treatment, a couple don't. Some provide enhanced treatment or dissolved metals. Some provide both TSS, dissolved metals, and total phosphorus reduction. Not a lot provide oil. So they're all different. And a key part of that is when we're talking about more or less effective, a big part of that is understanding the problem at hand and making sure the SSC BMP that you pick matches. Okay, so longer question. So what is the threshold below which implementation of a given SSC project activity type might not make a difference? So there are no readily definable thresholds below which implementation of a given SSC project activity type might not make a difference based on the literature reviewed. There are probable thresholds of actions below which there would not be measurable or observable changes in downstream receiving waters. So there are actions that you would take, that, especially when you're at the beginning of your retrofit process and there's not been a lot retrofitted and a lot of areas are not managed or inadequate, you're not going to see as much of a change there. But if you're thinking about your retrofit in terms of the whole watershed area and reaching an ultimate goal, any action that removes pollutants or reduces flows on any scale will, when combined with other related actions, make a difference, even if it's not measurable in a stream using available methods. So you may have a very large project going and you may not see a big difference when you try to measure it, but you have to really think about the cumulative effects of the project, as well as the impacts due to unmitigated projects in a watershed that resulted in these cumulative effects of degradation and multiple projects, and may not be related to any single action. So you got to think about how you got where you're at, and also thinking forward to watershed improvements result from the application of one or more incremental retrofits or restoration projects under a single plan. So therefore, the threshold size is related to the cumulative benefits of the total plan that can be anticipated to achieve an expected outcome. And the existing watershed conditions can also influence the threshold. For example, treating the first 10% of a highly developed watershed may have a different observed benefit, not make a difference, meaning you won't measure a difference, than treating the last 10%, which will make a difference. And you might see a much larger reduction or improvement in both hydrology and water quality. So a couple of key points that we'll then highlight back on the flow chart relate to the threshold size, being related to the cumulative benefits of the total plan in the watershed that could be anticipated to achieve an expected measurable outcome. I combine these two, and then we go to the graph. Okay. I can't, when you have these Zoom calls, I only have so many screens, so I can't see everything anymore. Let's see. So for question 2A, another question we were addressing that's very much related to the last one is how much many are needed to achieve benefit, and or at what scale is modeling necessary to quantify benefits? So there is no standard answer to how many are needed to achieve a benefit at a given scale. As described in the response to the last question, watershed improvements can result from the application of one or more incremental retrofit or restoration projects under a single plan, or can occur over many years before being fully implemented. Also, the existing contributing basin size or condition may influence the threshold. So a useful metric that could be used is the percent of progress made toward the watershed goal. So if you're thinking about your watershed as in the improvements is one big area, maybe the easier way is just percent progress towards your complete goal. So modeling, in response to the question about is modeling necessary, modeling is a helpful planning tool that can be used to target for improvements or restoration, as well as identify gaps that need to be filled to achieve the expected benefits and to project the ultimate expected outcome, but may not reflect or confirm the efficacy of a specific action at contributing basins. So this last part's really addressing the fact that as you're beginning these progress, you may not see that benefit because it takes a lot more, usually to be done, many projects, those cumulative impacts there. So highlighting the watershed improvements can result from the application of one or more incremental retrofit or restoration projects under a single plan, and then over many years. And then going back to our flow chart, thinking about those variables that can influence the benefit for the SSCs and influence the application. And really for this one, it's really thinking about the whole thing, the whole watershed, those cumulative actions that are done over many, many projects. Okay, two more. And then we go to the matrices. So this is response to question 2B. How can the metric be scaled for retrofit projects that due to the project constraints are not able to fully achieve the defined stormwater related environmental benefit? So in the literature reviewed, we did not find research that provided any type of basis to quantify a partial BMP or a partial SSC project activity type, meaning a SSC that doesn't meet the full design criteria to provide the full benefits. So it's been reduced from that full criteria. However, there are common practices to scale metrics that are used. A lot of them assume a linear relationship between the portion of the SSC that meets the criteria to the portion of the benefit. A good example is the equivalent area determination. So if you've applied for a water quality grant, you've probably gone through that calculation before, or received a water quality grant for retrofit project. There's guidance in the Appendix 12 of the permit for Phase I for SSC 1 through 4. They use the equivalent area to measure benefit. It provides some type of framework to account for that partial benefit achieved by the SSC. So there's nothing out there, so we made suggestions for how to move forward. The equivalent area approach could be expanded to scale other SSC metrics, such as infiltration for flow control projects, pollutant loading for water quality projects, or normalized cost for any project. For SSC types such as property acquisition, restoration and repairing buffer, forest cover, or removal of impervious surfaces, modeling is commonly used to estimate flow control benefits. Specifically for this case, in relation to the metrics, it could be used, the results from that could be used to scale the metric by determining the portion of the post-implemented SSC flow rates to the same SSC size to meet the full flow control standard from the Stormwater Management Manual for Western Washington. This is an area where you definitely need more research. There's many you need more research on, but definitely I think we scale quite a bit, and this is an area that we could use research to better understand the accuracy of some of the methods that are commonly used and also identify ones that may be more accurate for comparing benefits. Okay, so when we're thinking about scaling benefits in the scheme of these variables that influence the application, right down in here with the scaled metric, this partial benefit concept is on here to determine that benefit of the SSC, and it specifically talks about that partial BMP size and estimating what that benefit is based on sizing and if there's any other influence that could limit the SSC's performance. And understanding that information will help you understand the effectiveness of the SSC and be able to compare what's more or less effective between the SSCs. Okay, last one. So what are other limitations, considerations for the most beneficial application of specific SSC project activity types for various locations, land cover, land use, and receiving waters? So based on the gaps in the literature reviewed and the number of project-specific variables that we've been looking at on the flowchart that influence the benefit of the SSC project activity type, it is not possible to determine the most beneficial application of specific SSCs. However, the literature does provide information that helps us with qualitatively understanding it, and we know which conditions can influence it. And we can use that information as a guide to focus more on what's a more beneficial SSC project activity type when you're comparing it to other SSC projects. And this is considering the unique project conditions as well. So as we talked about, noted previously on the table I showed you, SSC BMPs have different treatment and flow control functions, and they're not all the same. They're not going to provide the same. So really coming to an overview conclusion, the more beneficial SSC BMPs provide the flow control and runoff treatment function needed based on the receiving water and contributing basin conditions, those impact factors, and have proposed site conditions that are suitable for constructing the BMP without reducing the SSC stormwater related benefit. Other variables to consider include selecting SSCs that provide the other environmental benefits. Again, those are benefits that are not in the permit. So if you're looking for the more beneficial, you could also dive deeper into what are the environmental benefits from that particular SSC and will they be beneficial to the receiving water conditions, and also avoid any SSC that leaches pollutants, specifically if it's discharging to an impaired water body. So those are variables and considerations with thinking about more beneficial SSCs. And looking at where this all fits on the graph, really important to consider those unique project conditions in the receiving water contributing basin, the proposed site conditions, as well as the SSC to really help understand which one's more beneficial. And going through the whole process where the last box you get to is to figure out which one is more or less beneficial or effective. And then there's also, if nothing works, going back through and starting over with your site selection or BMP. So, okay. Can you see it? So we wanted one table that we could summarize all the data that we had collected here, and I am going to blow these up in just a second. So, but we did go through, I broke them out of the SSC groups and really started looking at them more as individual like BMPs or SSC BMPs instead of a group. Let Let's look at it a little bit closer in the upper corner. What we have is down the column, we have the SSC BMPs, all the different ones that we found in the literature summarized there. Then we have the hydrology performance indicator, as well as the water quality performance indicators. And the ones I have shown here are just for parameters that are in the NPDES permit, such as TSS, dissolved copper, dissolved zinc, total petroleum hydrocarbons, and total phosphorus reduction. For each, we've summarized the N. We have that not on this one. It shows up on another one, believe me. At the N, the average performance indicator for this one, it was % reduction. And here we do have the standard deviation. I think I talked about the min and max earlier, and that was on the matrices we developed for chapter 3. And then we have, so just looking at bioretention and phosphorus, what we have for the hydrology performance indicator, what's noted here is just straight out of the Stormwater Management Manual for Western Washington, what they're approved for related to flow control. And then looking at the treatment performance indicators that are defined in the manual as well. And that's what we used for any BMP that was in the Stormwater Manual. There are lots of footnotes that go with this table because there are lots of variables that can influence it, such as TSS reduction with porous pavement. You have to have the medium grade sand underneath it in order to get that 80%. So that there's lots of little notes that go with these. So then I've switched over to, I've left the column the same on the SSC BMP type. And now I'm just looking at the TMDL parameters. These are all the ones that popped up in the permit for what permits for Western Washington. So we go into total nitrogen, fecal coliform, E. coli, pH, temperature, and look at the different the sample size. You can go through and see the average reduction. If it's red and negative, it was leaching based on the results we had and the standard deviation. There's quite a spread in the study results for a lot of these. And these are, we did go through and we did pull outliers. We did try to get data that we had to be closer to what was in taped so we could have more comparable data and reduce some of the things that may not be as comparable. What we didn't do is some of the BMPs that are listed here, they're Washington BMPs and they're BMPs from North Carolina or Minnesota or whatever was uploaded on the International BMP database, and they may have a different design criteria and may perform a little bit differently than ours. So there's because there wasn't enough information on specific Washington BMPs to pull that together and have that information. So it was just to Washington. Oh, here we go. Okay, so the first one, again, I walked you through that without pulling the bar up, and then highlighting bioretention and porous pavement. They both fall under that new LID BMP. I think it's a SSC type 3, and just highlighting the different performance between them and the data we collected. Okay, so now I've cut the chart off. I've gone back to the left. I've got the SSC BMP on the left column. These are looking at ones that are not structural BMPs that you won't see in the stormwater manuals. Like we have property acquisition, open spaces versus commercial, and then the same property acquisition, open space versus industrial, and open space versus residential. So we couldn't find any data just on property acquisition. We couldn't find any data on restoration of forest cover because apparently nobody's monitoring runoff from forested areas. So in order to have some comparison with those, what we found is the next closest thing. Specifically for property acquisition, we found data for open spaces and compared that to presumed commercial development. So if it wasn't left undeveloped and it went commercial, what would we expect to see based on that data? And so we did a comparison between the two. Same with industrial. We compared, kind of industrial land use and runoff from that to open spaces and so forth with residential. And so that we have quite a bit more data here. I think that was from an SPU study that we were able to pull this from. And develop a good comparison to see what those benefits might be for this particular BMP. We do have quite a few that we weren't able to get data from. Restoration of forest cover, we really couldn't get good water quality data. And it was noted in the literature that there's not a lot out there, right? So, oh, okay, and that is it. I've got 4 minutes. Do you want me to take questions or you want to wrap it up?
I got a few minutes, Amy. So if anybody